Welcome everyone to the April version of the GoldSim monthly webinar. My name is Nick Martin with GoldSim Technology, and today's topic is going to be sensitivity and optimization in GoldSim. Feel free to ask questions or raise your hands at any point, and hopefully I will see those and get to you promptly. So let's go ahead and dive right into our presentation for the webinar. All right, so this first slide just shows a brief outline of what we're going to cover today. We're going to start out by talking about optimization and specifically calibration, or using mathematical optimization for calibration. And then we're going to talk about some advanced calibration techniques and how you can use these with GoldSim. And finally, we'll end up with sensitivity analysis and statistical measures in GoldSim, which are complementary topics to optimization and calibration. All right, mathematical optimization. An optimization problem consists generally of maximizing or minimizing a real function by systematically choosing input values from within an allowed set and computing the value of the function. This is kind of classical mathematical optimization. You may remember it from your calculus classes way back when. So it's maximizing or minimizing a value for a function, and this mechanically in GoldSim works fairly simply. You select an expression element, or could be a different element value perhaps, but to maximize or minimize based on changing other selected element values in GoldSim across a specified range. Of course, you'll want the target expression, the one you're maximizing or minimizing, to be a function of the other elements or other values or parameters. Otherwise, changing those input parameters will not have any effect on the thing you're trying to maximize or minimize. So often there is just, mathematical optimization, sort of conceptual or mathematical optimization is, something that generally with sort of a dynamic model, this would normally come into play with model calibration, and that's really where we generally be interested in it. Of course, there are other reasons you might want to use optimization for sure, and those tend to be more of a statistical analyses thing. So but they are definitely just pure mathematical optimization can be very useful as well. But pretty much for the rest of this webinar, we'll talk about optimization in relation to model calibration. So how that works is usually you have an objective function, which is what you're optimizing. And in the case of calibration, typically you're trying to minimize the sum of squared errors. And usually those sum of squared errors, that would be the squared residuals, where the residuals are the difference between the observed value and the simulated value. Okay, and so if you minimize that sum of squared errors of your model's fit to observations, this is one criteria for providing a best model fit. And it doesn't have to be your objective function, your sum of squared errors. You can be pretty creative in how you would extend or expand that. For example, you can apply penalties or bonuses, and those, of course, would just come into your objective functions as, a penalty would be an addition to the sum of squared errors, and a bonus would be a subtraction from it. Again, you're trying to get the minimum value of your objective function, which in calibration is normally the sum of squared errors. All right, so just to show sort of a simple illustration of calibration, and this is from a GoldSim model, and we'll look at this model in a minute, but you have your data values, the red dots, and your function, and this is your calibrated function, the blue line, going through your data values. And so you'd be choosing that blue line so that the difference from the data value to the line at that particular point in time overall across all the data values is minimized. Okay, so the figure I just showed is from a GoldSim model library model, and you can see the address for that model if you'd like to find it later. And let's open up that model right now and look at it for a minute. So give that a minute to come up for everyone. All right, so this is the model. It's simple model fitting to data is what we call it in our model library. And so let's just look through the model briefly to kind of set the stage for what we'll talk about in relation to optimization, and specifically calibration. So you see we have an objective function we're going to minimize. Okay, this is the sum of squared residuals. These are our squared residuals, and that's just a data value minus the calibrated function value, or the the modeled function value, and those are squared. And the deal with squaring them is you that way you get a measure of the absolute distance between the two. If you just had the data values less the function, then you would have positive residuals and negative residuals. And if you just added those up without squaring them, you could, of course, have everything cancel out, even though you had a very poor fit to your data. Okay? So let's look in here at the data. And you can see it's just a time series. And if we look at the data values, you can see we have 8 values, and they're at a specific time. And you can also notice that, we don't have any decimal points on here or anything like that. So we just have 40, 26, 20, and so forth. Okay. So if we go back up, now let's look in the model. So this container has the model. It's a very simple model. Here's our function. And you can see there, it's just a function that is an expression using these 4 parameters, which are what will be calibrated, and then there's the addition of this C2 value. Okay, and this one is not included in the calibration. All right, so that's pretty much what we have here. This model does, if you happen to download it and go through it yourself, it does have a nice dashboard to use. I'm not going to use that too much in this particular overview of this model because I'm more concerned with the mechanics of what we're doing. So to do an optimization, go to the Run menu, and there's an optimization option. Bring that up. That brings up our optimization dialog. So the first tab here, define optimization settings. Of course, very important. You always want to set your goal. In this case, it's minimize. We're doing a calibration. We want to minimize the sum of squared residuals, and that's the objective function that's chosen. You can add a required condition, where that would be a true-false value, and that would be a required condition for the optimization calculation. And you can also select precision, high, medium, low, maximum. All right. Now here are our optimization values. So these are the ones we're going to change to try to minimize our objective function. And so if we look at this first one here, you can see it's the C1 from the model. And we have started lower bound 0, initial value 15, upper bound of 100. So that's the range we're going to change this value over. And so we'll change these values independently to try to minimize the sum of squared residuals. And that essentially is what we're doing in this calibration. One thing that's be a good thing to point out here is, of course, that GoldSim has the context-sensitive help menus. If you hit this help menu right here, it, of course, first comes up to the screen for what you're doing, which is very good. But then, anything you would want to know about using optimization in GoldSim, you have a link to how to specify the optimization values, considerations related to precision. You look on related topics, you can see finding a global optimum in complex models with multiple optima, okay? As well as optimizing a probabilistic model and several other topics that will be of interest. Just real quick, finding a global optimum. So this goes through, and we're going to look at this. We have it set up to randomize optimization sequences and what we're going to run now. And so what that means is, as this algorithm goes through trying to find the optimal values, it's possible it may find one a local optimum rather than the global one. And so if you run it several times, you'll potentially get different values, and we'll look at that. And that's one way to look at finding or making sure you find the global optimum. Okay. All right, so we're going to go ahead and run this optimization. It's pretty simple. We just go to the Run Optimization tab and use the Optimize button. There you go. All right, so here we go. You can see on the left, and this is showing, I think, our top 10 results. On the left, you can see the minimal value of sum of squares. Well, I guess slightly more than 10, maybe. No, it's 10. And then the values that were used to get that optimal sum of squares, which in this case is a minimum value. And so that is sort of the mechanics of an optimization in GoldSim. Very simple, pretty easy to use, and there's a lot of times when this could be pretty helpful for you, I'm sure, in your models. So now I want to use this, use these results here to talk a little bit more about kind of advanced calibration and some considerations that you might want to take into account when you're really doing a calibration. So the first thing you probably already noticed is that sum of squared errors is about 39.9, so we'll say 40. Okay. So that's just to be, so we have, our sum of squared errors is 40, so we're definitely not 0. 0 would be a perfect match. So we do have at least some systematic error in this optimization, in the sense that, all models are wrong. Our model's not going to perfectly match the data. There's going to be some systematic error in there. In this case, we're looking at, looks like, well, let's run this again just to show you that we might get slightly different results. We have 39.9762, and this time we get to 40.1772. So this is the thing of finding, local, and in this case, well, the difference between 39.9 and 40.1, is that significant? Probably not. And so that's kind of what we're going to talk about in relation to calibration here, or using optimization for calibration in the next few slides and as we continue through this presentation. So I'm going to close this up, and so just remember, we're saying our sum of squared errors is 40. Okay. One last note sort of on optimization in GoldSim. So like once you go to exit this, you get this sort of save or exit optimization options. And oftentimes when you have the optimized value you want, you would copy optimized values to element definitions like this. And then you would run the model. And then that has, put those optimized value in your model, and now you can get results from the model with the optimized values. Okay. So one last note here before we move on. We're going to go back and look at the data. So we have 8 data points, and our sum of squared errors is 40. And so what that means is our average squared error is about 5, which means our average squared error is about 2.25 meters. So in that context, your optimization isn't really, we can also run this here. We'll run the optimization one more time. We've copied the values. Let's just see. So in that context, the difference between 39.9 and 39.98, 39.977 and 39.98 is really, with an average error of 2.25 meters, that has no meaning really. They're really not significantly different. Okay, so that's one thing to keep in mind. All right, so to kind of develop that thought a little further, we're going to go back to the presentation now, and we will go back to the presentation now, and we'll continue talking along those lines. All right, so that's we just saw this optimization model in GoldSim, and you can see listed on the page here is the optimization algorithm, the journal article behind the algorithm back in 1965, and that you can get this reference off our website as well, I believe, if you'd like it. So, optimization and calibration. Optimization is maximizing or minimizing the value for a function by changing the values of function inputs. With calibration, generally we're minimizing, and we're minimizing usually the sum of squared errors, but maybe sort of an advanced sum of square errors that includes weighting and bonuses and penalties and things like that. And so really calibration is using sort of optimization principles, mathematical optimization, to find the best fit model parameters or the best estimated model parameters based on minimizing that sum of squared errors. Okay, and that best fit is simulation results to measurements. So in this page, basically we have our same 8 data points from we were just looking at in the model, but rather than points, measured values, a measured value is usually, it's measured multiple times. There's some amount of measurement error. So there should be some, actually spread in what an acceptable, or, the measurement doesn't really give you a point value. Okay. And so that's what we're showing here with the box and whisker plots. So with that in mind, we can talk about real calibration. So if you're calibrating a model representing a real and somewhat complex system to real or actual data, you need to incorporate additional considerations relative to just purely mathematical optimization. Okay, so as we saw with the box and whisker plots on the previous slide, we don't expect real measurements necessarily to provide exact values, but usually there's a range, there's multiple measurements. Depending on what the measurement is of, it might be kind of a derived measurement, and so it might have fairly big error bars. And so this means that, what this really means is that you're, there's kind of two things. You're minimizing your function, you're minimizing your sum of squared errors, but you're not necessarily minimizing it to 0, right? So we know that there's going to be some systematic error or some error in just the general conceptual match of your model to your system, which is always going to be there. It's not, if you have a significant amount of data and it's a complex system, you're probably not expecting an exact match. So you have some systematic error. Beyond that, you also have some error, some expected error or range of values, result values, that you would expect based on your analysis of your data, what you have in terms of, okay, I have, what are my error bars? If I propagate that across all of my data values or my measurement values that I'm using in the calibration, what does that, add up to? And so what those two considerations give us is that it gives us, there's the sum of squared error threshold, okay? And so what happens with the sum of squared error threshold is we're going to say we can consider any realization that comes in below that threshold as a calibrated realization, okay? So we don't have a unique calibration in most cases, and or a unique set of calibrated parameters. Rather, there's significant uncertainty there, and you have a range of these that provide, your range of these that provide your acceptable fit. And you don't have necessarily, when you start, a good way to know which one of those is the best. Okay. So we could have a, if we arbitrarily set our sum of squared error threshold in that example model we saw, we could set it to like 40, 41, something like that. Okay, and then we'd say all of those values of the parameters we were calibrating that provide sum of squared errors below 41 we're considering calibrated. Okay. So conceptually then what you have, and this sort of simplistic plot showing that, okay, hey, I have all these, I have these data values. I have some uncertainty related to what these values are. So, all of the lines represented in this sort of crude figure would be, equally viable calibrations. And this is another sort of example of this concept. This comes, I think, sorry, it's kind of an old figure, but it comes from a groundwater model, I believe, a large region-wide groundwater model, many different data values, and so you can see there's a fee threshold on here, and that is that's set at 8,000. You can't really see it, but it coincides with the top. And so analysis of the measurements behind this model that we're being calibrated to suggested that, we could expect there was that much uncertainty expected in our sum of squared error because there were, hundreds of measurements that were calibrated to, and they were different types. So maybe you have stream flow, and you have to, if you have like discharge, you're calibrating, this is a groundwater model, so in this case, the calibration was probably both to head or water levels as well as to discharge. You have to scale those values to get your sum of squared error on the same basis so you don't overweight one versus the other. And we don't necessarily need to go into that, but that's just explaining why that threshold was chosen. And so you can see there is an actual calibration, and that calibration occurs as the blue line. So that's the sum of squared errors for that, what was considered the actual calibration. And then we have all these other acceptable calibrations specified by the green dots. And so there's 100 of those that we've got that come under this threshold. And so really what those represent in this case, just because of the model that was used underlining it, is, it's in a large way, it's like different spatial parameterization. So we're saying we have different, we have not a complete data coverage of our area that we're simulating. And so there's some places we don't know what the values are for the input parameters. And so in there could be a range of values that could be selected that, since we don't have data, would allow you to, essentially get a different realization of your system that is also, calibrated. So it's, for what we know at this point, it's equally valid. Okay. All right, so continuing on to talk about sort of real calibration, because real measurements provide a range of likely values and not an exact value, there's usually not a unique calibration or unique set of calibrated parameters. This also, obviously I've been listing measurements, but there's also a system error, like, all models are wrong, so your model's not going to exactly match the real system. There's always going to be some component of system error where, this is as good as you could do with your conceptual understanding of the system. Okay. If you do have 100 non-unique calibrations, so you've minimized your sum of squared errors or your objective function in your calibration below the threshold, then you have a range of calibrated values for each parameter. So you have a range of values that are acceptable for each input. This is based on your data uncertainty. And you also have a range of model results that are calibrated. Okay, so you have a range, sort of both inputs and outputs. And the thing to think about here is, usually if what you're interested in solving for your model is a different value than what you calibrate to, right? If you had data on what you were really interested in, you wouldn't have to do the model in the first place. So, usually water flow models, various sorts, you're calibrating to water level measurements because that's what you can get, and what you're really interested in is discharge or flow. And so that's your result value, okay? So, and the one thing sort of now we're kind of going to start coming back towards GoldSim a little bit. So as I said, you have a range of both your input values and you have a range of your calibrated results. And you have these ranges, that essentially gives you a probability distribution. So these would essentially be, this is one way to get your GoldSim model inputs. So let's look at this a little bit more. All right. Um, but before I continue on, just threw this in as a reminder to myself. Just a note with real calibration. So we saw when we looked at the, we've talked completely about the sum of squared errors in this and minimizing that value. As you probably all know, or all of you who've done numerous calibrations know, just minimizing the sum of squared errors, that's not enough analysis of your results. You always need to plot your residuals. And again, here what you're doing is you don't want individual bias in your residuals. Okay. So if there isn't any bias, your residuals should be normally distributed with the center of mass of the distribution at approximately 0. And of course, your observed versus simulated values, you always want those to plot along a one-to-one line. Again, showing that the variation is random, essentially. So it's always very important to look at your residuals in addition to your sum of squared errors. And if you have any sort of spatial component in what you're doing, you need to plot your residuals on a map as well. And so those are just sort of coming back to the calibration things to keep in mind, and things that will catch you in review if you don't keep them in mind and look at them. Okay. So it is important to look at the individual residuals as well as the sum of squared errors. But so now I'll continue back sort of along how our topic here in terms of sort of real calibration using a threshold and sort of the advantages that could generate for you. So all of these sort of topics that I've presented beyond the just mathematical optimization, obviously these are not my ideas or anything I developed. If you want a very good reference on these things, how to implement these things, you could implement them in GoldSim if you wanted. GoldSim's fairly general. You can also use, other parameter estimation models, which tend to be model agnostic in the sense that they'll work with any other model. So you can kind of do that either way. But this is a good reference for advanced calibration and parameter estimation, and will give you sort of the details of what I've been glossing over from 100 miles up. All right. So the main point was showing sort of these, how you can have a threshold where you're considering multiple calibrations valid. Is, the point here is, your model will have some error. You're not going to get a unique value, really. You're not going to get a unique calibration. Saying that, oh, this calibration with sum of squared errors of 39.97 is better than this calibration with sum of squared errors of 39.9 is really, you're at risk of basically overfitting your model and then sort of coming up with a unique calibration that, because it's overfit, could actually be uniquely wrong. With this advanced approach, really, I think the big advantage to, sort of this calibration with, multiple calibration realizations below a threshold, especially in relation to GoldSim, is this is a really good way to incorporate 3D model results into GoldSim. Okay. To do your, risk analysis or performance analysis of a system. What you get out of this approach, this sort of advanced calibration and parameter estimation approach, is essentially probability distributions. And those, as we all know, come into GoldSim very easily and provide a great basis for, a way to look at more risk and performance analysis. And it's, definitely one of GoldSim's biggest strengths is the ability to both incorporate and propagate this type of uncertainty. And so we often get questions of, oh, how do I develop probability distributions for my model inputs? And, how do I link a 3D model to GoldSim? And I would suggest that this is one of the best ways to do it. Okay. All right, so we've talked about optimization, pure mathematical optimization, and using optimization and calibration, which is, how you would probably be most interested in using optimization generally with GoldSim. Now let's go on, and we're going to talk a little bit about sensitivity analysis. This is largely sort of the same sort of, or is a largely complementary complementary concept to calibration. So normally, so the sensitivity of simulation result to a particular input is the amount or degree of change in a simulation result achieved from incremental changes in the input. Okay, and normally, well, what we're really looking at with a calibration is we're looking at, changing the parameters that are most sensitive across a range to find the range of those sensitive parameters that best match our data. Okay. It is equally, or it can be equally valuable to know which parameters aren't sensitive. And that would be the case of, you could change these parameters, these inputs quite a bit, and you wouldn't see much change in your result. Okay. And so knowing that a model isn't sensitive is also very important. It could tell you that there's some issue with model formulation. If something you thought was supposed to be the main driver of your model is actually not having much impact, then that's one thing that might tell you, somewhere something was missed in the formulation or something like that. And it also could tell you, if the model formulation is fine, of course, then it tells you, well, you don't need to worry about this parameter too much, just pick a representative value and it's not really impacting your results. Worry about the other parameters that are. Okay, so sensitivity analysis, this is one that you often see in various modeling scenarios, more probably groundwater flow than others, but it's a standard guide for how to do it. Basically, it says, the model's been calibrated and used to draw conclusions. You want to do a sensitivity analysis to identify which model inputs have the most impact on the degree of calibrations and on the conclusions of the analysis. And so the idea here is, you're trying to maintain calibration and seeing which ones have the most impact and what does that mean for your analysis. And the idea of maintaining calibration and sensitivity, this plays directly back towards having a threshold that you're calibrating under to. That is actually, that whole process is actually telling you quite a bit about the sensitive ranges, the sensitive range of analysis for your parameters, which are also ones that are important for you because, if it is a parameter range or, it's outside of the range that's leading to a calibrated model, essentially what you're saying is, well, it's less likely that that part or that parameter range, that part of the parameter range is applicable in this case because you've said, well, it doesn't lead to a calibrated model, so ergo, it's not as important, or it has a lower probability of being important. So kind of a classic example of this is, a water flow model is calibrated to water level measurements. Sensitivity analysis will look at changing input parameters so that the model remains calibrated. So our sum of squared errors doesn't change significantly, remains below our threshold. But what we're wanting to see is, how does that change our volumetric outflow rates? Okay. And so we saw this on the this plot on the right was on a previous slide, and I didn't talk too much about it. But so this is essentially a result of a calibration below a threshold. So, and it's actually showing flow measurements. And so you can see you have what was listed as a calibration, but the other lines, numbered 1 through 5, are also calibrated realizations. And so you can see we have these calibrated realizations, which means we've changed these input parameters across some range. And you can see the change in the result we're looking at, which happens to be a flow rate in this case. And in that chart, there are negative flow rates, but it is flow is considered a vector. Negative is either in or out, I don't remember. And positive would be the other direction. And what that approach leads to, where you have these ranges, is then you get a histogram, right? And so the histogram is shown at the left, and once you have a histogram, of course, you have a probability distribution. And one thing you can do, and especially in the name of sensitivity analysis, is that you have this is your calibrated range of flows. And you can see it goes from 100 to over 200 liters per second. You could also, if you wanted to extend this for a more robust sensitivity analysis, you can add outliers to essentially put tails on your distribution. Very easy to do. Okay. So we saw one use of sensitivity analysis, which was looking at how, parameter values could change while still maintaining your calibration. So like how much, given the uncertainty we have in our system, how much wiggle room is there going to be? There is also another very good use of sensitivity analysis, and this is also often more of an exploratory type of analysis. And basically you just change, parameters through their known range and see how the solution changes. And this often occurs pre-calibration. And so you'd vary the parameters through a known possible range and look at a result or solution variation to determine which parameters are most important. The one sort of drawback with this approach is if there is little uncertainty in the value of the important parameters, then knowing what will happen for unrealistic values for your particular system may not be that helpful. Okay, so this is a classic sort of sensitivity analysis plot. You see we have normalized values for our parameters, and so we're showing the range of these parameters and what that means for the results on the y-axis. And so, it's showing you, for example, that the C parameter is fairly sensitive in terms of impacting the results, in the sort of lower normalized portion of the range. And so now let's go on and let's look at sensitivity analysis in GoldSim. And this is another sort of component built into GoldSim where you have a nice tool built there to conduct this sort of classical sensitivity analysis for you. And this model I'm going to show now, and we'll step through a look and just look at sensitivity analysis in this model. This model we're going to show is one of the example models. And so as you know, the example models come with GoldSim, and you can access them. If you have GoldSim installed on your computer, you have these example models installed as well. So let's go and look here. Okay, so the model just came up here. And so this is a simple sensitivity analysis model. So we look at this. This is just an image, but we'll look at the actual sensitivity analysis dialog in a second. So here we have our result to analyze. And you can see, it's calculated from these 4 parameters. 3 of those are stochastics, and 1 is a data value. And so this is all that's in this model. Very simple, very straightforward. But if you want to run sensitivity analysis, you go up to Run, and go to sensitivity analysis. And here you go. So you would set your result to analyze. In this case, that's X. And then we have, our independent variables. And so you can see with the stochastics, you get this nice thing where you can just set probability ranges, percents essentially being the probability ranges. And you can also, for the data value, you're setting an actual physical range. You have these little plot icons here. These are actually buttons. So you click on one of those, you can see, here is the range that we're gonna look at for that parameter. As with all things with GoldSim, you have a context-sensitive help button here. So always a good thing to do. You're doing a sensitivity analysis. Just click the help button. It'll walk you right through. And things you should consider, what you need to do, all that good stuff. It's pretty straightforward, but there will be topics pretty much for everything you would want to know as you go through this. The ones that are probably most relevant or probably most important to see would be the tornado or the charts, and then of course the central value result, And this goes over, it just lists for you, what goes into that analysis. It's always good to look at this so you know, okay, this is what we did. There we go. All right, so we could do calculate to calculate the central value result. This came up for us already. Then the other things you would normally be doing here, in addition to setting your result to analyzing and adding, your independent variables, and you can do that with these buttons, would be your charts and of course your result data. So let's look at the result data. So this just ran through the analysis and shows us, where we're at, our points. Okay. And then there's the XY chart, which we already saw in one of the slides. And then, of course, there's the tornado chart. The tornado charts are kind of cool. Nice to see. These shows that C is the most sensitive or has the biggest impact on the result. It's at the top. The one with the lowest impact, D, is at the bottom. The tornado charts are helpful. It's kind of involved explaining this. I always recommend, just go look at the help real quick and you can see, oh, here, the tornado chart. What is a tornado chart? It's pressed by hitting the tornado chart button. Very good. All independent variables are held at their central value, and it runs 3 deterministic simulations with 3 different values, lower, central, and upper, repeated for each independent variable. The results give you this chart. Pretty straightforward. So again, the help menu, the context-sensitive help menu is always there, and definitely, especially for sensitivity analysis and optimization, there's enough different switches and plots produced that it's always a good idea to keep looking at those. All right, so that is pretty much sensitivity analysis in GoldSim. In terms of sort of the built-in, sort of dialogue-based functionality, of course, GoldSim is a very sort of general framework, so you're not restricted, ever just restricted to these built-in dialogues. GoldSim will do pretty much any calculation. If you want, you can, implement that calculation yourself if it's not already built in. All right, so we'll go back to the slideshow here for a minute and sort of wrap up the last few topics. And we have a couple questions. I'm going to hold off on those questions. We'll get to the questions here at the end real quick. So it'll just be a few minutes. We're almost done. So just hold those questions for a second, guys, and I'll get back to them. So here's the tornado chart again, and we went over that briefly. All right, so sort of kind of last overview of the sensitivity analysis tools in GoldSim. So we saw we have graphical analyses you're getting from the dialogue, essentially the tornado diagram and the XY plots. And then we have statistical analysis, and that's what we'll go over in the next few slides, but these come from running a Monte Carlo analysis, and essentially you're getting to these values out of the multivariate element. Okay, so we'll look real quick at those statistical features or those statistical calculations you can get for Monte Carlo simulation. And so here we go. This is another model library model, and it's a fairly simple model, but all we really want to look at here is just this result, which is a multivariate element result. Produces a scatter plot chart. If I run this model, then we can look at this guy, and so here's our chart. We get a value for each realization, so that's why it's a Monte Carlo simulation. And then from this, there's a variety of other menu options, and these are where you get to your statistics. There's, of course, the table of the final results. You could also have capture points in here. And then there's a correlation table showing the correlation between the two, sensitivity, some sensitivity measurements, I'll go through quickly in a few slides with what each of these are, so we don't go through them in too much detail. You can, of course, use ranks, which is a very nice feature. You just do that, and so that's rank-based rather than value-based. Okay. And another good thing to look at is the setup for the multivariate result. So you set your result, and then you set your variable 1. If you add other things, obviously if you add x1, x2, x3, you'll get actual tables here with 1, 2, 3, and however many values that you added to it. Okay. There's the correlation table, and that of course would expand too if you added additional parameters. Okay, so that is sort of the access to those statistical features for the Monte Carlo results. And we'll go back to the slide and we can just briefly go over what those parameter or statistical values that we looked at were. So we had the coefficient of determination. I'm mostly putting these in slides here, I'm not going to go through it, the definition word by word. You can, that way it's there. And if you want to look at the presentation later, you have it there to read. Of course, the context-sensitive help menu will give you that information as well. So coefficient of determination is the fraction of the total variance based on linear regression, importance measure, fraction of results variance that is explained by a variable. Correlation coefficient can be rank or value, and it describes the extent of the linear relationship. Standardized regression coefficients are normalized measure of the linear relationship. And then partial correlation coefficient, extent to which there's a linear relationship between the selected result and the input variables. Okay. There are, of course, many more details on those particular statistical measurements in the help built into GoldSim, as well as the GoldSim manuals. I don't want to abuse your attention spans by going into those in great detail, but they're always there, and there's plenty of references to look those up. All right, the final thing, now we can take any questions, and just a note that there will be a video from this webinar posted to our website, likely tomorrow, but maybe as late as Monday. And so that'll be available whenever you want. So now there's a couple questions, and we'll go into those now. Feel free to stay around for questions if you want, or otherwise have a good day. And thanks for coming. All right, so in terms of questions, I got 2 questions. Tornado chart is a measure of local sensitivity, though not a global sensitivity that you get with the important measurement. It is, yes, somewhat localized, and we can, yes, it is somewhat localized, and of course you're not getting, obviously, the across realizations or anything like that. It's more of a deterministic localized analysis. And so is that just a fancy tool for doing one at a time? It is pretty much one at a time, and we can, yes, so yeah, let's say it's a fancy tool for doing one at a time. Okay, so if any other questions, thanks again for coming, and I'll be online here for a little while for anything else.